name is Michaela, and I am a biomedical engineer at BTS Bioengineering. We're about to begin our webinar on the jump assessment of wearable devices. Welcome to our webinar for the jump evaluation provided with the GWalk. The GWalk is our portable system for motion analysis, which is a wearable IMU device. Before going into details of the jump test, I'd like to give a brief overview to understand the importance of the test in evaluation of athletes. The athlete's evaluation is essential for coaches and sports trainers who aim to maximize the performance of an athlete while safeguarding physical health. The development of individual training programs makes it possible to define training regimens, such as setting targets and monitoring the achievement of results, prevent injuries, minimizing the risk and assessing the return to sport process, and provide the athlete with objective data to motivate and encourage them. For a complete functional assessment of the subject, it is essential to integrate the evaluation of the physiological and functional parameters. In a previous webinar, we discussed the importance of biomechanical evaluation of gait. For those who haven't seen it, you can go on the BTS Bioengineering website and the webinar page. Today, we'll investigate the functional vertical jump test. Why the vertical jump? Well, this test is commonly used to evaluate athletes in sports such as basketball, baseball, high jump, and other sports because the vertical jump, single or multiple, allows you to obtain valuable information on muscle strength, aerobic capacity, and reactivity. When we talk about jump tests, we need to keep in mind that there are different types of jumps. In this context, one of the most famous and well-known test batteries is the Bosco test. The Bosco test includes counter movement jump, squat jump, counter movement jump with arm thrust, repeated counter movement jumps, squat jump with body weight, drop jump, and stiffness test. Jumps can be evaluated using different measuring instruments. The most common tools are rulers or meter sticks, video analysis, or inertial software. From the graph, we can understand how, as the complexity of technology increases, the number of parameters obtainable and the accuracy of measurements also increases. Today, we are focusing on the use of inertial sensors in the evaluation of the jump test. I will now do a quick practical session and show you how the software and the G sensor can be used. This is the sensor positioning. The sensor must be positioned below the line connecting the two venous dimples. The sensor then needs to be inserted into the belt and tightly secured to the waist of the patient or athlete that you'll be doing the test on. I'll now show you the software and give a brief overview of how you would do a test. As you can see, we first connect the device via Bluetooth. Then we can select the analysis protocol that we'll be using, which will be the counter movement jump to begin with, within the several Bosco tests. We begin a new counter movement jump. And once we press start, there'll be a quick stabilization phase. After the stabilization phase, the acquisition of the test will begin, and you can instruct your patient to perform a counter movement jump. Once it is complete, you can press stop and save, and a report will automatically be generated where you can see different metrics such as the height, the acceleration graphs, and this page is also modifiable so you can change the different graphs in the different views. Next, we'll do a squat jump. So once again, we'll start a new jump. Then we'll start the recording of the data. Again, we'll have this quick stabilization phase of the device and the acquisition of the movement. In this case, it'll be a squat jump. Once the movement is complete, we can stop, click OK, and save. And once again, the report is automatically generated with multiple parameters. You can see in the bottom left, the elasticity is shown because we just recorded the two different tests. We'll now go over the reports, and I'll show you how the different parameters are explained. As you may have noticed, the test is simple, quick, and automatically provides reports with indices such as the elasticity, Bosco index, coordination, endurance, and task, which is the reliability of the assessment, and the work decrease, which is the potential reduction of elastic energy production over time. We'll start with the counter movement jump, and we'll go into more detail on how this jump is performed in the analysis as well. The subject begins in a standing position with the feet shoulder width apart and the hands on the hips. Once the operator gives a signal, the patient begins to do a downward counter movement, bending the knees at 90 degrees. The jump action is achieved thanks to the stretch shortening cycle. This test aims to investigate the explosive force and power of the lower limbs. In fact, these parameters represent an important component in many sports, especially those that require high explosive strength, such as volleyball, rugby, and other sports like that. Usually the jump performance is evaluated by measuring the height of the jump. But as we can see, the GWAP gives us very useful parameters, and many more than just the height, to characterize the jump, providing an automatic measurements, strength and power, forces in the takeoff and contact, maximum concentric power, takeoff speed, and impact. Next, we'll go over the squat jump. The squat jump is similar to the counter movement jump. However, once the test is begun, a subject performs a squat by bending the knees 90 degrees and maintains that position for 1 second. From this static position, the subject performs a vertical jump without the downward counter movement. In this jump, the counter movement impedance allows to evaluate the rapid force and the capacity of the neuromuscular system to overcome the resistance of the high contraction capacity. Also, in this case, the sensor allows us to obtain information on forces and powers automatically. By comparing the squat jump and the counter movement jump, it is possible to calculate the symmetry index, which evaluates the ability to store elastic energy during the counter moving phase of the counter movement jump. The shortening stretch cycle of the counter movement jump allows the muscle to create more contractile energy and therefore on average increases the jump height by 10% compared to squat jump. The values of the symmetry index, however, are strongly dependent on the type of sport and therefore present different reference values. Next, we'll go over the counter movement jump with arms thrust. The subject begins the test in the standing position again with feet shoulder width apart and arms at side. Once the operator gives the signal to start, the subject begins the jump by doing a counter movement jump downward, similar to the counter movement jump, and then jumps with the help of their arms. In this jump, the jump height is usually increased by the swing of the arms. The correct use of the arms leads to a more rapid contraction of the muscles in the lower limbs, increasing the height of the jump itself. Optimizing the use of the arms, therefore, means maximizing the jump performance. The contribution of the arms during the jump is evaluated by the coordination index, which normally in athletes has a value greater than 15. Another interesting application of the vertical jump concerns the evaluation of the characteristics of metabolic processes in repeated short jumps, such as for a duration of 15 seconds, in order to evaluate anaerobic lactic capacity and the power that corresponds to resistance to the fast force or ability to overcome resistance with fast contraction. This parameter is evaluated using the endurance index. An index with a value closer to 1 indicates that a subject expresses high levels of explosive force. It's possible to evaluate the anaerobic resistance or the fatigue strength by performing jumps with counter movement lasting 30 seconds to 60 seconds. If the index value is closer to 1, the subject has a good resistance to fatigue. Next, we'll go over the squat jump with body weight. By combining the results of this jump with the previous squat jump, we can calculate the WID index that represents the force-speed ratio and allows us to evaluate if the workloads are appropriately managed during the squat. If the index is high or more than 0.3, it means there is a reduced explosive force capacity. And if the index is smaller than 0.3, it indicates a reduce in muscle mass. Athletic trainers and coaches can use this index to identify points to focus on in training, as with the other indexes. Next, we have the drop jump, in which the subject begins in a vertical position on a step, with a height ranging from 20 to 60 centimeters, with the feet shoulder width apart as always and hands on the hips. Once the operator gives the signal to start, the subject begins by extending a leg and dropping it forward. Once the subject contacts the ground, they immediately perform a vertical jump. This jump investigates the reactive explosive force. Finally, we have the stiffness test. The stiffness test consists of the subject repeatedly jumping over and over again for a set duration, depending on the sport. This test shows the consistency within the different jumps, and as you can see, shows the different parameters for each of the jumps, so you can compare them within that time duration. It is therefore clear that using the sensor for an assessment such as the Bosco test, we can obtain objective information that can't be obtained by just investigating the jump with a meter stick, ruler, or video analysis alone. The jump analysis with the GWalk allows the athlete to be evaluated and to define training programs involving the athlete and thus increasing motivation for training.